Welcome back, everyone. I'm Professor Rhett Smith for ProtonGuru.com. Today we're covering Lesson 4.17. It's our last lesson in Section 4 of the book dealing with reactions on aromatic and pi-conjugated species. And here I'm going to talk about an interesting reaction that involves formation and reaction of diazonium salts. Now, diazonium salts are given the formula R with 2 nitrogens plus, and we'll draw a Lewis dot structure of that in a second. They're very good precursors for a variety of transformations into other functional groups. And you can make the diazonium salt from an amine. Pretty easy to make if they are on an aromatic ring. One thing you have to be very careful about is that diazonium salts are pretty dangerous to handle if you don't have specialized training. So don't go off trying to make these on your own if you're not in a specialized lab with specialized training. But a well-trained individual could react an aniline that could have R groups, and this line going from the R to the middle of the benzene just indicates that you could have this R group ortho, meta, para to the NH2 group. It doesn't matter. NH2 reacts with hydrochloric acid in the presence of sodium nitrite. That's NaNO2. And you've got to do this at low temperature. Again, very dangerous if you warm these up to a warmer temperature. And what that will do is create the diazonium salt. So any R groups could be on here, and you would have the diazonium salt, which looks like this. Now, the interesting thing about this is that this diazonium salt, it's written out here, when reacted with a variety of different, usually metal salts, can replace that N2 group, N2 coming off as nitrogen gas. It replaces that group with some group attached right where the nitrogen used to be. So these R groups stay right where they were. All you do is replace the NH2 group with some other group. And a variety of different metal salts can be used to put different groups onto the ring. If I use copper chloride in this step 2, then I replace my nitrogen with this X group, where X is a chlorine. If I use HBF4, I can put a fluorine on in place of the nitrogen. Copper bromide, bromine. Copper oxide, I actually put an O on, and then that gets protonated to make an OH group. If I use potassium iodide, I put an iodine on in place of the NH2 group. If I use this phosphorus acid, I actually put a hydrogen on where the NH2 group used to be. So why would someone ever go to this trouble and danger of making these diazonium salts to do a reaction like this? Well, let's say we're trying to make this compound. We're trying to put 3 bromines and iodine on a benzene ring in this particular isomer. You might say, well, okay, I'm going to take my iodobenzene, which I can buy from a chemical company. I'm going to react with Br2 with iron bromide. Well, I'm going to have the first bromine directed ortho or para to that iodine. So maybe it goes ortho. Now I have the second bromine I want to put on, right? I'm trying to put 3 bromines on. Well, I have 2 ortho-para directors. So the iodine directs the next group to go here or here. The bromine directs the next group to go here or here, ortho or para to it. So there's no really good directing ability of this compound to force the next group to go somewhere specific. Consider, on the other hand, if we start with aniline and do a bromination reaction. Now, aniline has this NH2 group, which is an activating group. In fact, it's so activating, I don't even need to add the FeBr3. I can just use bromine to do this reaction. If I do that, my NH2 group will direct the first bromine to go either ortho or para to it. It will still direct the next bromine to go ortho or para to it because it is still a stronger activating group than the bromine. It will still activate only the ortho or para positions here. It doesn't activate the meta position, so you're unlikely to get bromines there. So that is a way to get the 3 bromines to be positioned around the ring like we want them to be in the initial target. But our target has an iodine here, not an NH2 group. And now you see that we can, in the very last step, make the diazonium salt and use potassium iodide to replace that NH2 with an iodine. And that's how we can get the specific target we were looking for in the beginning. So now that we've seen all these different reactions for placing groups on benzene and replacing those groups or changing those groups after they're placed on the benzene, we can now start to design our own synthetic pathways to complicated molecules that take more than one step. I'm going to start out by showing you how to design syntheses for two relatively simple molecules here. And when you see a proposed target and they're telling you to start from benzene, you want to think about a couple things. First, most of the reactions we learn to put groups on the benzene ring are electrophilic aromatic substitution reactions. If we have to start with benzene, there aren't any groups on there yet. So let's see if we know electrophilic aromatic substitution reactions to put these groups on. Bromine and a nitro group. Yes, we can put both those groups on with electrophilic aromatic substitution reactions. Now that we know that, we need to decide which group to put on first to get this meta isomer, right? The bromo and nitro are meta to each other. And you can sort of think backwards and think, well, if I put the bromine on first, it will direct the next group to go ortho or para to it. But that's not what we want. Well, what if we put the nitro group on first? The nitro group is a meta-directing group. So that is what we're trying to get in this case. So thinking about the planned synthesis, we would want to first put on the nitro group. The nitration requires that you use nitric acid and sulfuric acid, and that will place the nitro group on first. Next we need to put the bromine on. This requires using bromine and either iron or ferric bromide as your Lewis acid, and that allows you to put the bromine with some selectivity for the meta position. It's a good exercise to try to pause the video and see if you can figure out for yourself how to make compound B. And the thought process is really the same. First, can I put both of these groups on with the electrophilic aromatic substitution reaction? Well, I can use a Friedel-Crafts acylation to put this group on, and a Friedel-Crafts alkylation to put this group on. So yes, in this case, we can still place both groups using electrophilic aromatic substitution. And in this case, we're targeting a para isomer instead of the meta isomer we targeted over here. Which group do I need to put on first to get the para isomer? Well, let's say I don't have the methyl group on first and I put this acyl group on first. That's a deactivating substituent because it's got this polar bond. So that would direct the next group to go meta to it. Well, we don't want that. What if we have the methyl group on first and we put the acyl group on second? Well, the methyl group will direct ortho or para to it. So we'll get a mixture of products, but at least we'll have favored the desired para product as one of the two we'll get. So that thought process tells us we want to put the methyl group on first, and we need to have the chloromethane as the starting material. Remember that the chloro group will be ripped off by the Lewis acid, aluminum trichloride, in the Friedel-Crafts alkylation case. And in this acyl group, pretty similarly, you need to have the acyl chloride with the aluminum trichloride to pull that chlorine off to make the acylium ion, and that's how you would get the target product. So the first reaction puts the CH3 on. Now we already have the CH3 on. In the second step, when we put this, we'll get a mixture of ortho and para products, but this is the best we can do to get some of this material as a major product. What about a case like this? Some of these targets that we'll see have groups that we can't put on directly with an electrophilic aromatic substitution reaction that we've learned. So can I put both of these groups on using electrophilic aromatic substitution reactions? No, we didn't learn how to put a carboxylic acid functional group on. We did learn how to put a nitro group on. Well, how could I access this carboxylic acid group? One thing we did learn is that you can take a benzene that has a methyl group on it and use a strong oxidizing agent like potassium permanganate to convert the methyl group to a carboxylic acid. So on a piece of scratch paper or something, I'll write down, I need to do this step in addition to whatever other steps to put the groups in the ring in the first place. So in the end, I'm going to need a step to put a methyl group on, a step to oxidize the methyl group, and a step to put the nitro group onto the ring. Well, what do I want to do first? Well, if we can put the nitro group on with electrophilic aromatic substitution, let's think about that as the first step. Well, nitro is a meta-directing deactivating substituent, but we're after the para isomer, so we can't do that first. And we can't do the oxidation step until we have the CH3 group on the ring already. Well, let's try putting the CH3 group on the ring first. So scribble this out and say, what if I had a CH3 here as my first step? Well, CH3 is an ortho-para director, and we want the next group to go para to the CH3. So if we go down here and start sketching out our proposed synthesis, we could have chloromethane with aluminum trichloride. Okay, we put the CH3 group on here. Do I want to oxidize it first to make the carboxylic acid? Probably not, because then if I put the nitro group on, it would be directed meta. So I don't want to do that as my next step. Instead, I want to do my nitration. So we have the nitric acid and the sulfuric acid, reagents required for the nitration. We already had the CH3 here. And we're going to direct that to go ortho or para to the existing substituent. In this case, I'll just write plus some ortho because here we're keeping the para isomer and taking it forward to the next step. And that last step will be converting the CH3 to the carboxylic acid that we want in our ultimate target. So we'll have potassium permanganate, KMNO4, and the nitro group down here. Of course, we'd have carried through some of the ortho product as well, but this is the best we can do. Well, now let's examine this case. And again, the first thing we need to figure out is whether we can put both of these groups on with electrophilic aromatic substitution. Surely we know to do a bromination to put a bromine on the ring, but we don't know a reaction to directly put an NH2 group on the ring. We do know that we can reduce a nitro group, a group that we can put on the ring with electrophilic aromatic substitution. And we can reduce that to the NH2 group using something like hydrogen gas and palladium, or we could use HCl and iron or HCl and zinc, a variety of different things we talked about in our oxidation reduction topic. That means we need 3 steps. We need to put on the nitro group so that it can be reduced to the NH2 group, and at some point we need to put on the bromo as well. Well, the bromo and the NO2 group are the groups we can put on with electrophilic aromatic substitution. Which one will we put on first? Well, in this case, the product we're targeting is the para isomer. If I put the nitro group on first, the next group will probably go meta to it as the major product. And that's not what we want. So we'll probably need to put the bromine on first and go from there. So if we start with benzene and we put the bromine on, next we need to put the nitro group on, right? One of the steps is reduction, but we need the nitro group to be reduced. We're going to get a mixture of the ortho and para isomers. Here I'm just going to say we're going to keep the para and we'll have some ortho we remove through a separation process. And finally we do the reduction. We can do this relatively simply if we just use hydrogen gas and palladium, although you could use HCl and tin, or HCl and zinc, or HCl and iron. A variety of different metals will facilitate this reaction depending on your conditions. Any of those cases, though, will take the NO2, reduce it to the NH2, and leave the bromine alone, and that's how we get the target product here. So these 4 examples show you how you can think through putting groups on, what order they need to be put on, and sometimes transforming a group that's on the benzene ring using one of the other reactions we've learned.